Welcome to today's webinar with the title Basic Design Rules, Layout according to the Würth Elektronik parameters and the PCB fits. I am Andreas Schilp, your speaker of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. And now I wish you lots of fun and new information. So we are celebrating 10 years of Würth Elektronik PCB webinars. And this topic we are talking about today is one of your top 3 you have selected and originally offered in May 2013. And it's even current, more current than ever. So recently we worked on our basic design rules and had an update. So the original webinar in 2013 was attended by 47 attendees. So meanwhile, there have been a lot of changes in our logo, in our corporate design, even our characters have changed to titanium. And of course, last but not least, we have a totally new website. And I can really recommend to have a look at our new website. So this is the agenda for today. First of all, I will talk about the difference between basic and standard. So I think it's important to have a common understanding about these two words. Then I will introduce into the new basic design rules, scope of application, contents, of course, and what is new or different. Afterwards, I will give some background information on the changes, why we have changed this, and especially for 3 points covering processes for copper structuring, specification of copper thickness according to IPC, and aspect ratio for drill holes. And last point, I will give you an example how to use the new basic design rules. So let's have a look at the definitions of standard and basic. So standard is a category or classification. So standards are often used. Think about paper size. DIN A4 is a standard. And as well, we have standards in all technologies. So it's a category or classification. It's not a technology. And standard classification is available from all PCB plants. It's available at a favorable standard price. Other categories are advanced and sometimes even leading edge or state of the art, which is more or less a niche classification. So standard and advanced are available in all technologies. As it's not a technology, it's a classification. This is an example, an excerpt out of our design rules for slim flex technology. Here you can see technical, standard, and advanced requirements, so the 2 different categories. And you can see differences in the values, of course. So that's just one example and fits for all other technologies as well. So further examples for standards are, for example, standard stack-ups. So this offers advantages as we are using material in stock. We have standardized processes. So this ensures high quality, favorable prices, and normally short delivery times. Now let's have a look at the word basic. So definition of basic, it's a technology. And by basic technology, we mean single-sided PCBs, double-sided, and as well multi-layer printed circuit boards. So this is a technology, and it's divided, of course, into different classifications or categories. So within basic, we have as well standard and advanced classifications. So basic is the technology. Another tip for using standards. Standards are the basis for quality and efficiency in terms of error prevention, increased productivity, reliability, and last but not least, safety. So we also have standard layer stackups, as already mentioned, also digital for import in your EDA tool. We have the standard design rules, we have standard delivery specifications, standard packaging, and so on. Let's have another look at the basic technology. On the picture, you can see the variant multi-layer. So it's a rigid board. It uses one layer of, or it uses prepreg outside, prepreg and copper foil. So within we have cores. The layout should be according to the basic design rules, and is, if possible, use standard stackups with standard material according to standard delivery specification in a standard packaging. So this is basic technology in the variant of multi-layer. So this is the new flyer, basic design rules. The contents are scope of application, basic nodes, basic base material, basic standard stackups, copper structures and spacings, drills, drill pads, annular rings, clearances, edge plating, solder mask, peelable masking, and last but not least, markings. So now we have 8 pages. The old version had 4 pages, so we have doubled the volume in terms of pages. Hopefully, we have also added new content and improved the whole thing. Basis of the new basic design rule was a bachelor thesis with the topic digitization of design rules for improved production data of printed circuit boards. And we orientated to the design rules of EDA systems, especially Cadence and Altium Designer. So let's see the scope of application. The basic design parameters as copper structures, spacings, hole solder mask markings, and solder surfaces. They are basically valid for all PCB technologies, so not just basic technology. So beyond basic, for example, also for HDI microwire technology, embedding technology, or flex solutions. So that's important. So as you can see here on these stack up pictures, of course, this shows an HDI stack up with several microwire layers, and so as well we have solder mask, we have outer layers, we have inner layers, we have bladed through holes. So for all these aspects which are described in the basic design rules, this also fits for HDI microwire. But of course, additional design rules have to be added, covering the special technology issues for maybe HDI microwire, embedding, or flex solutions. So let's have a look at the flyer. We can see the first 3 pages, and here you can find also hyperlinks to some documents on the new website, for example, standard stackups, technical delivery specification, contacts, and so on. So pages 4 up to 6, we can find information about copper structures and especially spacings. We will come to this point soon in more detail. We also can find information and rules covering drills, drill pads, annular rings, and clearances. And the last 2 pages covering edge plating, solder mask, pillable masking, and markings. So let's have a short look at solder mask, and the question is, why are wire holes exposed in the solder resist, in the solder mask? So on the right side, you can see a cross-sectional picture showing residues in a wire hole. This comes from the application of the solder mask, and if we cannot really clean this barrel from solder mask, that might cause some issues. The combination of increasingly smaller wire holes and shrinkage and expanding of the layers, as well as registration inaccuracies, can cause the resist maybe even to be exposed. So chemical residues may be clogged in the wire hole and may also damage the final surface, as you can see on the right bottom picture. There's also the risk for soldering problems, tin bits from solder bridges maybe. So all these topics will also be covered in the next webinar on the 8th of March. So I will not give more information about it, but the topic of the next webinar is plugging, filling, tenting, and we will also cover all these questions around wires and treatment possibilities of wires. Okay. So now let's have a poll, and this is a poll very similar to the original webinar 10 years ago. And what I want to know is what has the greatest influence on the minimum copper spacing. We are talking about subtractive etching technique on inner layers. Is it the number of layers, thickness of copper foil, thickness of the electroplated metallization, or the total thickness of copper foil and electroplated metallization, or finally the pre-break thickness? So now I start the poll, and you should get a blue window where you can make your choice. So what has the greatest influence on the minimum copper spacing? There's just one correct answer. We have passed 50% participation, so let's have another round about 10 seconds to give you the chance to make a decision. Okay. So now I will shortly close the poll and show the results. All right. So this is the result. 12% gave the answer number of layers, 41% thickness of the copper foil, and luckily most of you have chosen this correct answer. It's just the thickness of the copper foil, as we don't have any metallization during the production of the PCB. We just have the base copper foil, and this is decisive for the minimum copper spacing, and I will show you shortly why. 7% pre-break thickness is more or less quite vice versa. So the the pre-preg thickness has a dependency of the copper thickness. So if we have thick copper, we also need a lot of pre-preg to fill in all the spacings between the thick copper. So, but there is no dependency of the minimum copper spacing of the pre-preg thickness. So thank you very much for your participation in this poll, and let's have a closer look to the background of these things. So copper structures and spacings, we have to consider that the conductor spacing, or more generally, all copper spacing is crucial for the production of the copper structures. And this affects all features, as you can see here. So for the design of the conductor width, the line width, we have other criteria, not the production, but maybe current carrying capacity, or some specifications regarding signal integrity or permissible tolerances. So in principle, the conductor width can also be larger or smaller than the conductor spacing. For example, if it's possible to have 100 micron line and 100 micron spacing, it's even more favorable and more easy to manufacture if we choose 80 micron line and 120 micron space. So the larger the spacing, the more easy to manufacture. And regarding the line widths, the minimum allowed conductor width is 60 micron, as you can see in the table in the flyer. But for impedance-defined structures smaller than 75 micron, please consult us. So it's a question of tolerances which are allowed and process control. If we regard UL marking, so there is a value 4 mil, and below 4 mil, around about 100 micron conductor width, there is just the chance to make a marking according to UL 94, that means flammability. If you have larger conductor width, larger than 4 mil, there is, besides flammability marking, also a full recognition marking, let's say having CTI or MOT listings. So if you have questions regarding this point and need smaller line width, please ask us. So now let's have a deeper look into the basics of copper structuring. Let's have a look on inner layers. And for inner layers, there is a so-called positive imaging and a subtractive etching. What you can see here is in red the base copper on the base material, and the black rectangular shapes are your data, so customer data. Now for the etching process, we need a resist, which is green in this picture, and you can see that it's larger than your data. And this is the starting point where we start the etching process. So now the etching liquid can attack the copper, and the copper is protected by the green resist in some areas. And as the etching process not just etches vertically, but it's called isodrop, so in all directions, we also have an under etching under the green resist. And next step is removal or stripping of the edge resist, and here we are with the lines you wanted in your data. And the line width is measured at the foot according to IPC. So that's the final etched copper as it's standard in PCB production. And this is a new table for inner layers. So what's new here? We have, as already mentioned at the very beginning, we have different categories. We have standard and we have advanced category. And the values are different, of course. These are all values for the conductor spacing or copper spacing. And the last row shows minimum possible line width. So that just not have to be 60 micron, but it could be 60 micron. Of course, it could also be even much more larger, but the restrictive parameters are the copper spacings. And based on the starting copper foil thickness, ½ ounce, 1 ounce, 2 or 3 ounce, you can find the minimum copper thicknesses according to the IPC 6012. So that's also new. So for inner layers without plating or metallization, there is no difference between IPC class 1, 2 or 3. So it's all the same. And why is it less in copper thickness compared to the starting foil thickness? That comes from, on the one side, tolerances of the supplied foils. So there's an allowed tolerance of plus minus 10%, and usually we see the tolerance in the minus, not in the plus area. And as well, on the other hand, we have cleaning processes which reduces the copper thickness. So normally we have thicker minimum copper thickness compared to these values here, but that's allowed according to IPC. So now let's have a closer look at the copper structuring on outer layers. There is a different imaging, so it's negative this time, you will see soon, and there is a selective copper deposition, and there is a etching of just the base copper, which we already can see here. So again, red is the base copper here, and based on the base material. So next step is we need again a resist, and this time negative. So your customer data in black and our photoresist in green. This time that's a negative process. So we have to protect the base copper in the spacing areas. So the next step is the copper plating. So in between the resist channels, there is a growth of copper in this plating process. And the last step is we have to protect the new plated copper with a metallic resist. It's a tin resist, you can see in light gray. And next step is then to remove the photoresist, the green areas here. So now we have exposed base copper for the etching process. So we have a protection of the plated copper by the tin resist, and we have exposed base copper. So the etching process attacks right here. And again, it's not just a vertical attack, it's an isotropic attack again. So that's why the copper is removed also a little bit to the left and right side in this cross-sectional view. And so here we are with the lines you have designed in your customer data. And last step is removal or stripping of the tin resist. So that's the way how copper is structured according to customer data on outer layers by negative imaging, by a selective copper deposition, and by etching the base copper. And you also can imagine if the spacing is too less here, so it's very critical to make a good etching process and to remove the base copper completely. So if this would be too narrow, we could not have a chance to make the separation etching by etching here. So that's why the limitation is not in the first line the line width or the copper structure, it's the spacing which is important for the production. And here is the table for outer layers. Again, we start with the copper starting foil thickness, which you can find here. And now we have two different rows for IPC class 1 and 2 and IPC class 3. So the difference, as I already mentioned, is the different plating in the barrel. So for IPC class 3, we need minimum 25 micron in the barrel. This has also an impact on the copper thickness outside, of course. And here we can find the minimum conductor spacing in a standard classification here, and as well the advanced parameters. And maybe in the old paper you had, or definitely you had just one value. Now you have two values, and maybe you can find the best values now in the advanced section, in the advanced classification. But on the other hand, we can be sure that all the standard values could be produced in each plant from everywhere. Okay. Another closer look at plated through holes and vias and drill pads, annular rings, and clearances. And the decisive question is, why are annular rings needed around wire holes? So it's all clear for through hole technology, for pin connectors maybe, which are placed into the plated through holes and soldered. So for perfect soldering, we need annular rings. That's clear, but why do we need annular rings also for just electrical connections for wire holes? And that's not that complicated. You can see on the right side, sorry, one step back. On the right side here, you can see a lot of layers laid each one on the other. So this stands for different materials, different copper layers, and there is a registration normally by pins within the materials, but due to shrinkage, due to misregistration and tolerances in the drilling process, we finally get displacements on the different layers. You can see here, we can see 4 different wires with inner layers, inner layer pads, and there's displacement obvious. So these 4 wires are not close together, but these represent wires in the corners of the production panel. Okay. And the relationship between wire pad size, registration, and drill diameter has some impacts of the annular ring specification regarding IPC classes, influence of the drill tool, especially deflection. The smaller the drill tool, the larger deflection issues. We have influence of the machine itself, and last but not least, we have layout or design dependent shrinkage and expansion. And finally, the result of this is offset of layers relative to each other. So this picture is very important. The ideal situation on the left side is what you see on your screen if you do the design, but the right picture is more real and is allowed in total. Another important thing for drill diameter is the so-called aspect ratio, and we will see that on the next slide. So aspect ratio is a ratio, and first of all, you have always to clear what you are talking about. In this case, on this slide, we specify the aspect ratio by drill diameter B divided by the drill depth A. So B to A is in this case the ratio. It could be also vice versa, A to B. So be sure to talk about the same definition if you compare aspect ratios. And regarding aspect ratio for bladed through holes, there is a maximum ratio of 1 to 8. And why is this important? The aspect ratio is decisive for an even and complete metallization in the drill barrel. So that's important for the quality. And on the other hand, it's a possibility to calculate the minimum drill pad size. So here we have an example. We are asking for the drill hole and the minimum pad size, starting with a 1.6 millimeter thick PCB. So according to the aspect ratio, the smallest drill diameter could be 0.2 millimeter, and the smallest pad, according to that, you can see in the table, in the design rules, in the basic design rules, we get 0.45 millimeter for the smallest pad diameter. So this is the importance of the aspect ratio value. And here's the table. Some other remarks. So we have added aspect ratio here, and another thing is the copper clearance on inner layers without pad. So why this is important, I will show you on the next slide. The copper clearance on inner layers in planes, ground planes, for example, without a connection and without a pad. So why do we need copper clearance in ground inner layers without a pad? So we are talking about non-used or non-functional pads. On the left side, we have a complete stack with 6 layers, but we only have 2 connections on the inner layers on layer 3 and layer 5. So there's a chance to remove these pads on layer 2 and layer 4. And it looks like we now have got new space for design for routing in this area and this area, as the pads are no longer there. But remember the real life picture for the annular ring. So it also could look like this. So the barrel with less annular ring, so near to 0, but this is real life. And we have to also consider this situation. So if we got this situation, we actually see there is no additional room for design. We removed the not used or non-used or not functional pads, but there's no additional room. So it does not add space on inner layers if we remove these pads. And the next thing is, if you do a design route check, that must be done before the pad removal. Okay. So now, finally, an example for using these basic design rules according to our parameters. So this time we don't have a basic technology, as I already mentioned. These values are also usable for HDI technology, and especially in this case we have a flex rigid board with HDI in combination, and we've got an ultra-fine BGA 0.5 millimeter pitch, and this is the top layer design. We have 138 pins, not complete array, not full array, so some pins are free, and this gives us some more options for the design. Having a closer look to this section, we now can see this is a design with microwire in pad, and the microwire, for example, here is the pad is directly connected by a standard line, and here the line is reduced. So we not used from 100 design to 75 micron to 75 micron, so line width and space. But in this case, the design uses 70 micron line and 90 micron separation or clearance. So this enables also to cover the line with solder mask without issues, and gives us more yield in the production, so more separation, more copper spacing makes the production much more easier. So that's how we can read the basic design rules and apply them. This is a picture part of the PCB showing the footprint on the PCB. So now you can see how we made this in the real product. So let's have another poll. So now, after you have learned about the new basic design rules, I want to ask you to make a decision how many points on a scale of 1 to 10 do you give the new document. So 1 or 2 points would mean, in my eyes, it's totally unusable. 3 to 4 points may be incomplete and incorrect, which would not be nice, but okay. 5 to 6 points means the document is quite okay, but maybe incomplete. 7 to 8 points, maybe good, helpful, understandable, and 9 to 10 points, almost perfect. I use it often. So these are the decisions to make, and I'm starting the poll now. Okay, so we have passed 40% participation already. And I'm glad to see no one actually selected 1 or 2 points by now. That may change, of course. Okay, 70% participation, another 5 seconds maybe. And there is, of course, the partnership offer. If you think that that's not a good document, would like to come into contact with you in writing after the webinar, and also feel free to write me errors, additions, optimizations in the question field. So I will care about this definitely. Okay, so let's close the poll now and show you the result. So luckily, no one chose 1 to 4 points. There have been 16% 5 to 6 points. So there is, of course, the chance for optimization, and thank you for this. 76% quite good, helpful, understandable, and even 8% saying almost perfect. I use it often. So thanks a lot for this participation on this poll. So now we are already in the summary. What have we learned today? So we learned that the BASIC is a technology covering single-sided, double-sided, plated, and multi-layer technology. Standard is not a technology, but standard is a category or classification. Conductor spacing is more important for PCB manufacturer, and conductor width and conductor spacing should be considered independently of each other, and different values should be considered at least locally where it's needed. Annular rings around wire holes are still necessary, and non-used or non-functional pad removal does not save space on inner layers, especially on ground planes. And last but not least, Würth Elektronik webinars more than you expect.